All right, well, welcome back then. All right, glad you restarted that. Let's go ahead and begin the chapter then. And I'll race over to this side of the board here, find my markers, and say, all right, what is our new material? And so we are going to be starting here in chapter 18. And this is our first step of a series of chapters about electricity and magnetism. And this first step is about electrical charges and electrical fields. And to really understand what's going on, you got to kind of dive deep into a microscopic level. And to do that, we have to kind of review some science that we haven't covered together, but I think you've covered it in high school or middle school, and that's the structure of the atom. And so your author starts right here, it's figure 5, and he says, what does an atom look like? And this is perhaps overly simplified, but it's a nice picture of what we need. That is, there is a nucleus where there are neutrons and protons, and it's the protons we're going to focus on. In fact, I didn't even put neutrons on that board, but later on, I believe it's chapter 31, we're going to dive a little bit deeper into the structure of the atom, and we'll talk about the neutrons and other parts. But since that won't come into play for what we're talking about, let's ignore the neutrons. I think those are the green ones. Your author is trying to color those little green spheres and say those are neutral things. They don't have any charge, and that's why we're not going to be interested in them right now. And in fact, that's why they were not even discovered for a long time later, because they are neutral. And then the science just had no clue that there were other things in the nucleus. But it's what your author draws, these little purple ones that have a positive charge, and then these electrons which have a negative charge is what I want to focus on. And what I really want to focus on is each of them have charge, and that's where we want to start, this new property of charge. And again, probably not too unfamiliar with you. I'm sure you've talked about the structure of the atom and the charges that they have. And so we want to then take what you probably learned in high school or middle school and go a little bit deeper with this. But I want you to also recognize that the electrons are on the outside. And when I say on the outside, I mean way on the outside. That is, if you took this nucleus, which is really small, okay, and compared it to where the electrons are 100,000 times further out. A similar comparison would be to say if this nucleus right here was the size of our football field down here in the stadium, then these electrons would be over in New York. Okay, and so the reason I bring that up is because then if I take two elements or two substances, I'm going to take some vinyl and some acetate in a few minutes, and I'm going to bring them together and rub and scratch them, the things that hit are the stuff on the outside. It's the electrons. And that's what I want to get across. In fact, we do a whole lab on this tomorrow to kind of emphasize the things that move around, the things that bump around, the things that get scraped off are the electrons. And the protons are down in the middle, or in the nucleus. They don't move, at least unless the whole atom moves. So like in a liquid and a gas, they move, but not in a solid. Anyways, I hope I didn't spend too much time there, but I just wanted to make sure you kind of recognize this structure of the atom, because here's where we start then. We start with this idea that, all right, the atom is made out of many things, but just focusing on these two, the protons in the nucleus and the electrons on the outside, they have a property called charge. We're going to then give it a Q. And for those of you who've been with me since the Physics 110, you might remember that very first chapter, me starting to make a list. And I said, okay, over here on this side of the column, we'll put the new quantity we're going to learn for the semester or for the chapter. And then over here, we'll put the units that are used to measure it. And that's what I'm doing. And in fact, I haven't mentioned that really in a long time, since way back at the beginning of Physics 110, because everything we've been doing in Physics 110, we were combining our base units of a kilogram, a meter, and a second. You know, and then we had like kilogram meter per second squared and called it a Newton. And then we had a kilogram meter per second squared times a meter, and then we called that a joule. And then we had a kilogram a meter times a meter over seconds cubed, and we called that a watt, you know. And so we built up all these other units from those base units, but we never got anything new fundamentally until today. And so you're going to ask, well, what is charge? And I'm going to go, well, what is mass? Or what is a second? Now, that's not to say science doesn't understand math a little bit better than we've studied it. And that's not to say science doesn't understand charge a little bit better than we've studied it. It's just really a tough question. And one we didn't address. So we just said the proton has mass. We just said an object has mass. We didn't try to explain where it came from. We just said this was a fundamental part of nature. And I'm going to do the same thing here. I'm going to say an electron not only has mass, but it has charge. And so we're going to use the symbol Q. And we are going to then use the units called a Coulomb. And so just like we did for, I guess it was the joule and the Newton and the watt and the Celsius and the Fahrenheit, that Pascal, list goes on, we were going to give it a name in honor of the great scientists working in the field. And our first one is called Coulomb's law, and you're going to learn about Coulomb. And so in honor of Coulomb, we name the units after Coulomb. And without getting into too much of the history of it, if you took 6 and a little more, so I'll call it 6 1/4 billion electrons, and I know that sounds like a lot, but we're kind of back to, remember when we did a mole? Remember we did the ideal gas and we said let's group a bunch of these together, it's very useful. This is way smaller than a mole. Still a big number. And so 6 billion electrons is Coulomb's definition of 1 Coulomb, okay? And so that is a Coulomb. So it takes a lot of electrons, or at least I should say it sounds like a lot of electrons. Actually, that is quite a bit of electrons, at least a lot to separate them away from their nucleus. But that's 1 Coulomb. And so you're going to see 1 Coulomb of charge is actually quite a bit. But of course, here's what it means then, is that 1 electron then will have a charge of, and I'm going to put a negative. I said it a little bit quickly, but maybe I should have emphasized, and I'll demonstrate a little experiment done. But the charge of 1 electron is 1.602 times 10 to the minus 19 coulombs. And that's a good number to keep handy, you know. Put it in your notes, put it, I don't know, in the margin somewhere. But as you do the calculations, you're going to say, okay, I have 7 electrons, so how much charge do I have? Well, obviously it's 7 times that number, okay? Now, I'm also going to point out that 1 proton then has an identical amount of charge. And of course, it's positive. And so the two interact. And we'll look at a little experiment here by Franklin and some others that kind of showed all this. In fact, maybe now would be a good time maybe to kind of step away from the board and look at some of these early experiments that Coulomb and Franklin were doing here. And so I'm going to grab, I don't know if you can kind of tell a difference between these two materials. I'll hold it up to the camera too. One's a little clear and the other one's got a blue tint to it. Okay. Now, in my case, the blue one is vinyl, and I'll start there, and the other one, the clear one, is an acetate. Now, your book shows you the same kind of experiments here in figure 8 here, where they use amber. And so the early scientists realized that amber seemed to do this really well, and for their material that made sense, but vinyl does it a lot better, so I'm going to use vinyl here with the more modern material. But what would happen if I took a piece of vinyl and I rub it, and I got another piece of vinyl? I don't know if you can tell that this one's kind of blue and this one's kind of clear. Okay, and it's actually a little close. I'm trying to keep the moisture away. That's going to be one of our challenges being right here on the beach, is the water. We're going to talk about that. It has a big influence because it has electrical charges. And so some of these are hard to get working. Let me set this down. I should have done this one first so I didn't have to set it down. But if I were to rub this piece of vinyl, and of course rub this piece of vinyl, and then bring them near each other, I hope you will see something. And hopefully you see they repel each other. And this picture is showing really well what's happening here. Of course, here's the cloth. Mine happens to be wool. And of course I don't have amber, I have vinyl, and I rub it. And this is the part that I was saying, you've got to have that mental picture of what's going on a microscopic level, that there are electrons on the outside. And so what ends up happening is, if you can imagine one atom here and one atom here, and the electrons are kind of orbiting around, and you bring them together, and if you noticed, I rubbed it really hard. I squeezed with my fingers and was rubbing. In fact, in tomorrow's lab, that's what I'm going to tell you guys, is if you're not squeezing so hard that your fingers are not feeling like they're going to start on fire, you're not squeezing hard enough. And so it's that combination of pressure and sliding that what it does is it tears the electrons off of the atom, and so now they're free, but they want to go back. However, if you got two different materials, so wool versus vinyl, they may actually prefer one over the other. And so if you've taken 50 off of this and 50 off of this, as they go back, maybe this one grabs more electrons. So maybe this one gets 60 electrons, or 70, or 80. I'll just go to 70. So this gets 70, and then the other 30 go back over here. And the end result is, after rubbing them, you have more electrons on one of them, and the other one is lacking electrons. And so we did this transfer of charge. And if I were to do that for the vinyl, that's exactly what's happening. I rub this together, and the electrons actually end up coming off of this cloth and onto the vinyl. And so I would say that this piece of vinyl now is negative because it has more negatives than positives. Now, there's two things here I hope you caught in that discussion. Number one, did you notice what about the charges? Did you notice there's a principle here that we're going to call conservation of charge. Did you notice when I said we scraped off 100 electrons and then they went back, but one got more than the other? It was still 100. Did you see how I never said there was any electrons that were created? I never said, hey, there's more charges than I started with. There was exactly the same amount. And that's an important fundamental principle here when we begin. And so this first principle is called the principle of conservation of charge. And so we know that if you had 100 taken off and 70 go on here, then we can answer how many went back to the other one. 30, by using the principle of conservation of charge. And so you're going to hear that a lot from these next few chapters. I'm going to say, wait, that can't happen because, remember, conservation of charge. Those charges have to come from somewhere. Did you also notice, then, that when I called this one over here negative, I called it negative because it had more negatives than positives? Let me repeat that. Remember how I started? I started with a piece of vinyl. Remember the structure of the atom has a bunch of protons in the nucleus and a bunch of electrons. So when we said something was neutral, we meant it had an equal number of positives and negatives. It already had positives and negatives. And so when we rubbed it together here and transferred the charges over to here, this one we called it negative. And I want to emphasize, we don't call it negative because it only has negatives. We call it negative because it has more negatives than positives. But it has both. That's going to be important too in our thinking. And so never forget that. When you call something negative, it has both positive and negative. It just has more negatives. Now remember also then the other object, so I guess this would be my cloth, so I rubbed it like this. So my cloth would now be positive because it's lacking electrons. So did you notice then that this thing is positive because it has more positives than negatives? It still has negatives on here. There's still billions and billions and billions of electrons here. There's just a few more protons because we started with equal number. And so I'll say it again. Hopefully I'm not beating a dead horse too much here. But when we say something is negative or something is positive, we mean that they've got both positives and negatives. They just have more of the negatives or more of the positives. And an important part here, when we say this is positive, did you notice we made it positive by taking the negatives away? Remember I said earlier the electrons are on the outside, the ones that move and shuffle around. And so my warning for you is if you ever start thinking and you're going along a problem and you go, oh yeah, because the positive is going to move over, stop. Stop right there. The positives are not going to move over. The negatives are going to move. They're the ones on the outside. They're the ones that bump and rub. Okay, so let's go back to this little simple experiment here. So I'm rubbing these. I lost track of which side I had rubbed. Well, let me try it again. And one of the early experiments, and I think this was actually before Coulomb, so I think this was Franklin, who noticed that if you rubbed the like material, and he didn't completely understand what we just explained, but he knew that whatever was going on, it must be the same for both. And so he says here that these are negatives, and so two negatives must interact, and they must repel each other. But he didn't stop there. He tried other materials. So let me come over here and try the acetate. And I'm going to rub this. And let me just pause and talk about it on a microscopic level. And so as I rub them, again, maybe I scrape off 50 electrons off of this and 50 electrons off of this. And then because they got scraped off, they want to go back. But because they're different materials, they don't want to go back equal. One of them is going to be more if I can use a fancy word now, electronegative than the others. One of them is going to want to grab it back. And in this case, this is more electronegative. And so this ends up with more of the electrons, leaving this without electrons. And so now the acetate is positive. And now you can see why I had the two different materials. I'll say it again. Here, the vinyl sucked the electrons off of here really well. And so the vinyl became negative. But here, the opposite is true. The cloth is more electronegative than the acetate. So when I rub the acetate, I'm going to say that that is lacking electrons. That is positive. Now let me come back to my piece of vinyl again. And let's look at what happens when I have the negative from the vinyl and then hopefully the positive from the acetate. And hopefully you can see that they attract. And if I switch then to an acetate in my hand, and I rub the acetate, again, I'm going to scrape off, and the acetate's kind of hard to use. In fact, this will be my warning for you guys tomorrow in the lab. You got to really rub this hard, okay, until your fingers feel like they're going to catch on fire. And then bring it near. Maybe I should re-rub this one. A lot of moisture. It's starting to dry out. Getting cloud cover's gone. But hopefully, what you will see, which end did I rub? Oh, sorry. Well, this one's the hardest one to do. So let me. See if I can get it to repel. Aw. Might have gotten that one just a little too warm. I'm going to switch it. In fact, I might try. Sometimes I have better luck with paper. Oh. But I'm hoping to get you to see, good, that I can get to positive charges, slow down and push it away. And so the phrase we like to use is like charges repel. And so whether they were two negatives, like this vinyl here, or two positives, like the acetate, or a mixture where we had one positive and one negative, then they attract. And so again, the phrase is, and your author does a good job here in a picture, and so I'll kind of try to copy this picture. Where is his picture? A little further down, I think. Yeah, right here. He says this then, and maybe I'll draw a bigger picture, is if you have two negatives, they repel, or if you have a positive and a negative, they attract. In fact, I'll go ahead and draw a more, I think, thorough picture, because I think he should put all four combinations and say, all right, what happens here would be something like this. So if you have a positive and a positive near each other, they repel. But also, if you have two negatives, they also repel. And of course, if you have a positive and a negative, they end up attracting. And probably doesn't need to be drawn, but I will anyways. If you have opposite charges in the other order, they still attract. And so again, the phrase we like to use is like charges repel, unlike charges attract. And so we'll get to some numbers here in a little bit, but again, this is kind of this general idea of showing you this interaction of charge, these electrical forces. And this is going to be the groundwork for the next 3 or 4 chapters here. Okay, what's happening on a fundamental level here as we interact. And so like I said, this is why tomorrow's lab, this is what you guys will do. You will play with these strips and some other equipment here, which I'll kind of bring this one forward here so it can kind of get into the heat lamp here and start to be in a kind of a moisture-free environment, or at least somewhat moisture-free environment here. And so you're seeing, like I said, this principle of conservation of charge, and I would say then that what I have shown you so far is how to charge something by contact. Because I've been rubbing. I would also say, and I'll just show you this, you could charge something not necessarily by rubbing it, but just by transferring the charge. Watch this. Let me find my vinyl again. Okay, so here's the vinyl, and I'll try the paper first. Oh, and let me just kind of point out this, we call it a pith ball, because it's just a little tiny piece of material. Historically, it was actually pith, if you know what the old pith hats are from the African safari hats, you know, they're light and airy. Anyways, we use cork. So cork's pretty light also. So we take cork and we spray it with aluminum paint. So whether you want to call this a cork ball or a pith ball, but kind of by tradition it's a pith ball, even if it's made out of modern cork. But it's got an aluminum coating over it, and that's going to be important here because we're going to talk about conductors and insulators here in a second. But if I just come along here and I rub, and so again, maybe just as a review, what's happening here? Well, I'm scraping electrons off. And again, I'll just say 100 of them. It's probably a lot more than that. And then they want to go back. But vinyl loves electrons. And so they don't go back equally. They go back more on here than on the paper. And so this vinyl is negative. And so if I bring it close and touch it, I'm hoping you'll kind of see they repel now. Because what happened is it actually came over, it actually made contact, and then some of these electrons actually, when they got near that aluminum, jumped over and hooked onto that aluminum piece, and so now that aluminum is negative. So notice I'm kind of doing the same thing. I'm putting extra negatives on the aluminum, but I didn't rub it. And so I would put this in the same category, that I am charging something up by contacting it, and either by directly rubbing it, and so scraping them one way or the other, or having something that's already charged negative and then touching it. And so I have this negative pith ball. And see if I can get a few more on there. It can be a little hard to get them on the aluminum ball because this vinyl loves electrons so much that it doesn't really like to give them up. But fortunately, it's given up enough of them that I think you can see the interaction here. Now, with that in mind, let's try something else here. Let's look at this property. What if I charged it slightly differently? We call this charge by induction. And this one's a little harder to understand. You don't actually touch it, but maybe it's better shown with this piece, because this will help me also illustrate what is a conductor and what is an insulator. And so watch this for a moment. I'm going to take the vinyl again and rub it again until my fingers bleed. Okay, so get a good charge on here. But if you look carefully at what we call an electroscope, I want you to see this metal piece up at top. We call it a knob, because that knob is connected through a metal piece which comes down to, well, this solid piece, but also a movable piece. So we call these leaves. And the ones that can't move, we call it a fixed leaf. And the one that can move, we call it a movable leaf. Kind of makes sense. And watch something interesting. When I touch the knob, and try to put some on here. Maybe I'll switch back over to the wool. Ah, good. You see how the leaf moves out? I mean, what happened here? I mean, I never touched the leaves down here. I touched the knob. In fact, why don't I touch it with my finger and watch what happens? And now it goes back down. Why? In fact, what if I don't actually touch it? What if I just get close? But then take it away? Versus touching it and swiping it. Now, let me emphasize, none of this is charged by induction yet. I'm just trying to build up to that. Because I actually touched it. I would say I charged it by actual contact. I mean, I actually did swipe and touch it. Although the only thing that's different between this one and this one is that when I swiped on that one, I touched the knob. I didn't touch the leaves. And yet it seems to be something on the leaves that's going on, not something on the knob. And that's because, again, we're seeing quite a few things in action here. One of them is the third piece, which is charged by polarization. But we're also seeing the effect of a conductor versus an insulator. Oh, it's not a dry one. Where's the dry one? Ah. And so let me just put these words up here. What is a conductor? What is an insulator? And I'm going to put it this way. That a conductor means that the electrons can freely move through the material. But for an insulator, these charges, these electrons, are kind of fixed. They cannot move. And so when you actually set them in a particular spot on that particular object, they can't move. So luckily, as you probably saw here, this vinyl piece and the acetate is an insulator. See, what happened is I took my piece of cloth and I rubbed it, and right here where I rubbed it, the electrons jump back and they stay there. Can they move down to my hand and then go onto my hand and then go up my arm and maybe to my other arm or maybe down to my toes? No, because this is an insulator. The electrons stay exactly where they were placed. They're locked in, and so I took advantage of insulators when I was rubbing all of these. I rubbed here and said, okay, they're going to stay there. That's why when I set it down, I kind of set it on the edge and say, okay, they're going to stay there. They're not going to come back over to here. And then likewise, if I took my vinyl on here and I rubbed it, I took advantage of the fact that it was an insulator. And I said, okay, now that it's an insulator and I has a bunch of negatives right here, can those negatives move to the other side? No. Can they move up the string? No. And so I can then put them together here, and we can then watch the effect of two negatives near each other. But I didn't have to worry about them moving somewhere else. They were locked into place. And that's this idea of an insulator. Okay, but other materials, they conduct. And that means they move around. Well, let's come back over here to this electroscope. Remember when I touched it and the leaf went down? I would say it could do that because both me and the electroscope are conductors. Oh, watch this again. I'll come along and I'll bring it near the knob. Let me pause and not actually touch the knob. But don't you see the leaf move out? Let me pull it away. And the leaf goes back down. This is a good example of a conductor. Oh, let me try to draw a picture of this. You see, I have what looks like I'll call this the knob up at top. And as I was trying to explain then, there would be a metal piece coming down from the knob. Then it angles over, and this is the part that I called a fixed leaf. And said, look, that metal piece is so thick and made out of metal that even if you put a little force on it, it wouldn't bend or wouldn't move. But what was important was there was another one that was on a little hinge right here that is movable. And so we call it the movable leaf. And so when I brought the negative near this knob, let's look at this microscopic again. If I don't touch it, that means the electroscope is neutral. Okay, so I have a neutral electroscope. Now, I said this a while ago. You're going to hear me say it over and over again. If it's neutral, does that mean there's no charges? No, it means what? Right, equal number of positives and negatives. But watch something interesting. If it has not only an equal number of positives and negatives, but it's a conductor, that means it has an equal number, but they can move around. And that's exactly what's happening here. Is in this knob is a bunch of positives and negatives, but the negatives can move. It's a conductor. So if there's a bunch of negatives in this knob and I put the negative vinyl near it, what's going to happen to these negatives here? Yeah, they are repelled away, and so they will run away, if you will, and they'll race down to the other side of the metal piece. And so what will end up happening is both the fixed leaf and the movable leaf are now negative. Now, of course, I should probably emphasize that the knob must be positive because, remember, it lost those electrons. So the whole electroscope is still neutral at this point. I haven't actually touched it. All I've done is say the whole electroscope is neutral, and yet it moves out. And this is why. Because the fixed leaf and the movable leaves are each negative, so they repel, and the knob is now positive. And if I then pull the vinyl strip away, what do you think is going to happen next? Yeah, these negatives don't really want to be down here. They're only down here because the vinyl was chasing them away. You take away the vinyl, these negatives are going to go back up to the knob, and as they do that, the leaf will collapse back down. Okay. Maybe that was so much information in one shot, it's just worth seeing it again. And it feels kind of like it's picking up moisture here. So, if I get this right, I can hear it crackle. Okay, so I bring it close, and sure enough, the movable one moves out. But when I take it away, it goes back down. So it goes out, and so it moves down. That is, the negatives move down. The knob is still positive. The whole electroscope is neutral, and I pull it away. The electrons then go back up. And this is actually kind of an intermediate step. Remember, I'm trying to get to this big one here, what is charging by induction, but this is what we mean by a polarization. That the object is overall neutral, but one side of it is positive and the other side is negative. In fact, your author has a good picture for this. He shows, where's his polarization? Whoops, too far. Right here. And I guess B and C would be the model I'm looking at because I'm using the vinyl, which is negative. And it pulls. And in this case, he doesn't show like the whole negatives moving away. This one shows more of a conductor, so this is what would happen on a conductor. The negatives actually move to this side, leaving this side positive. So this would be like the knob, and this would be like the leaves. Interesting enough, it doesn't actually have to be a conductor. It could still be an insulator. You don't have to actually then move them a long distance, because within the atom itself, they just elongate. And so it has a net effect of having more positive this way and more negatives that way. And so it works the same way, whether it's an insulator or a conductor. In fact, maybe you can see it here with this pit ball. If I go ahead and I will touch it because I am a conductor, and when I touch that, if the electrons can then move, they will. The phrase we like to say is they like to go on the biggest object around, and that really just means the electrons, remember, they don't like each other, so they like to spread out. So if two conductors come in contact, they're going to want to go more on the bigger one. Now that doesn't mean all of them will, but I'm much bigger than this little pit ball, so they would much rather get on a big object like me because they can spread out than to stay on that pit ball, except for maybe the last one. So maybe one more is still remaining on there because that last one said, well, why would I leave? There's no reason for me to leave. I was only going to leave because there was somebody else here who was pushing me away. But as long as there is then two on there, they're pushing each other away. They would prefer to get further apart. And so they can go on my shoulder, and they can go on my hand, and they can go on my toes, and so they can really spread away. In fact, if I wanted to get rid of them off of me, I'll just touch something even bigger. And so a phrase we're going to use a lot is grounding. The biggest object around is the ground. Do I dare tell you a rude, funny story? Yeah, sure, why not, huh? I said this one time. This was before COVID. We were in lab. And I said, well, you got to just touch the biggest object around. And this guy said, oh, that'd be my sister. But, ooh, okay, well, that wasn't very nice. But anyways, so when you hear that word grounding, it doesn't really always mean touch the ground. It could mean something like this: touch something that is a conductor that is buried in the ground, because then it'll flow off of me and onto the conductor and into the ground. Okay? Notice it wouldn't do that normally because I've got insulator. I've got my shoes. I've got this rubber sole. And so it will not go on to the tile through my shoes. My shoes then are insulating me. And so I've got to make an effort to touch the ground. I guess I could go barefoot. Tile's a pretty good conductor, so if I was barefoot, then I would be instantly grounded to the tile. In fact, I'll tell you another weird story. This one's not just rude, this is just weird. I don't know what my parents were thinking, but we had this old refrigerator. We lived in an old house. And do you guys know what that third plug is? When you plug something in, and that third plug is called a grounding plug. And so if you have like a refrigerator or anything made out of metal, what you do for safety is you connect the metal frame of the refrigerator to that third plug. So when you plug it in, well, you probably can't see it, but there's a plug right here. This third plug right there, that wire, goes throughout the building, and in our building on the other side where the utilities are, that wire actually then is connected to a metal rod that's pounded 10 feet into the ground. And so it's the grounding wire, it's the safety wire. And so if you imagine this big thing was the refrigerator, so it was made out of metal, you would want to then connect the metal casing of the refrigerator to that wire, then plug it in so that if anything goes wrong inside of the refrigerator, like a loose wire comes loose, or a wire comes loose, and it touches this, instead of building up a charge so that when somebody comes along and touches it, they get electrocuted, it will then discharge and go to the ground. And that's hence why it's a safety device. And so most of your metal objects like refrigerators and washers and dryers, you know, they all have that grounding plug just in case something goes wrong. Hopefully that grounding wire is never needed. Well, when I was a kid, and I know this was a long time ago and the dinosaurs were still walking on the earth, okay, but when, we didn't have grounding plugs in our house. Those didn't exist back in the and this was an old house, so the house was probably built in the 30s. And so we just had the two wires. And so my dad cuts off the grounding plate on the new fridge and plugs it in. And we used that new fridge for years and years and years. And then something started going wrong. And it never affected my parents because they always had shoes on, but it was hot summer, and so my sister and I were always barefoot, and we would walk up and we'd be on the tile and we'd grab the refrigerator and go, oh, Dad, something's wrong with this. It shocks us. Of course, we didn't understand, but he'd walk up with his shoes and he'd go, nothing's wrong with this, it opens fine. Well, the shocks kept getting bigger and bigger, and we're lucky nothing went really wrong, because finally it got to the point my sister and I would learn that, okay, this refrigerator has a bad shock, and you only get it if you're standing on the tile. So we would like come in for a glass of milk or something, and we'd jump in the air and open the fridge and then grab the milk and pour a glass and then come back and jump in the air and open the fridge and put it back and jump in the air and close it. And we did this all summer long, and luckily nothing went wrong here, but I don't know what my parents were thinking. Money was an issue, I'm sure that was it, but it's like somebody could have really gotten hurt here, and luckily we didn't. Anyways, that's a little side story, and but what I'm trying to say here is you're going to use this phrase a lot. We're going to say grounded. We're going to be in the lab and we're going to say grounded, and so I'm going to say I'm going to ground this. So I'm going to come along and really not touch the ground, but touch myself, and if you just want to make sure I'm neutral, I'll touch the ground. Okay, so I would say this is grounded. Now, that means there's no more charges on it, or maybe there's one or two. But as I was trying to show here, you could polarize this pit ball right here. I can come along and I can rub this and watch what happens before I touch it. Do you see a little interaction? Did you see how it was attracted? Let me do it again. Because right here, I would say it's being attracted. Now if I touch it, and touch it hopefully a few times so I get some charges to transfer over, now they're both negative and they repel each other. And so that's what I was showing you earlier. And so the earlier one I was showing you is this, charge by contact. But this step right here, this is that polarization. This is where what happened is the negatives moved to one side of the pit ball and the positives were on the other side of the pit ball. And you might think, oh, well, nothing's going to happen because they are overall neutral. And sure, these positives are being attracted to the negative vinyl, but these negatives are being repelled. And you go, well, okay, one's being attracted and one's being repelled. However, can you see that the distance between the charges is different? Do you see how the negative in the vinyl to the positive is a shorter distance than the negative to the negatives? And so this is our first clue about Coulomb. Franklin's just getting conceptual ideas that like charges repel, unlike attract. But this polarization is kind of our first step to saying, what would be the formula for the amount of attraction? And it must have something to do with distance. Because clearly, a neutral object shouldn't be attracted to a negative, and yet it is. And so what I'm saying here is it is because once they get polarized, the positives and the negatives are closer together and they're attracted then more than these negatives, and these negatives are repelled. And so there must be some kind of formula that says, okay, how much interaction takes place depends on how much charge and distance. And that's what this little piece of polarization and charging by polarization is really getting at. Now, let's see if I can demonstrate it here, because I've got to go back to the acetate, which I hesitate with. Let me ground it again. But the acetate's the challenging one. But your author has this picture in A, and he does a good job here by saying, well, what if you brought a positive near it? And you don't actually touch it, but you just bring it near it. Is that going to attract it? Is that going to repel it? And I would say, even surprisingly, that it also attracts. So it doesn't matter whether you bring a negative near the pit ball or a positive near the pit ball. Because if you bring the positive, notice how the negatives move over and the positives go away. So you still have this separation of charge. That's why we call it polarization. But you're going to have the negatives closer to the positives than these positives are near those positives. And so you still end up with an attraction. Same thing. And so what I guess I'm trying to say is it doesn't matter whether you bring a negative near a neutral or a positive near a neutral. Once it gets polarized, you still are going to get attraction because it gets polarized in the other direction. And so let's see if I can demonstrate it here by saying, all right, can I get an attraction? Yeah. Oh, more than I thought. Okay. Now, if I actually touch it, of course, now it repels. And maybe I should pause here, even though this is exactly what you're going to do in the lab tomorrow. Why is it repelling now after I touched it? Remember, this was positive. And so it touched it. So did I transfer positives over to there? Yeah, that was that warning I said. If you ever find yourself going, oh, I'm moving positives, stop. You're doing something wrong. You are not moving positives. But what it can happen is, remember, this is positive because it lacks electrons. And so once this comes over and actually touches it, then the electrons could transfer from the pit ball over to here, leaving that positive. And so they are both positive right now, and so now they end up repelling. But if I neutralize it again by grounding it, and I have a neutral pit ball, you'll see it attracts until I touch it. And then it repels because they're both positive. And so that's that subtlety between what is a polarization and what is a contact. Now I know I'm still working towards this, right? I haven't really explained what is charging by induction, but all these steps then, I think, illustrate really well charge by contact, polarization, how a neutral one is attracted to either a positive or a negative, and then finally now, the induction will hopefully make sense. Because induction requires a third object. Not that we're going to necessarily pay much attention to the third object. But in this case, the third object will be me. So I will have the negative object, so here's the vinyl, and the electroscope, and the third object is me. Now before I actually try it, maybe we should look at this picture. So in picture A, we have two spheres kind of right next to each other that we can then separate. So I would say our three objects are going to be this. We've got a positive rod, and I'm going to use the negative one because mine works a little better. And then we start with the two together. And when you bring the positive rod near it, notice it will attract over the negatives to this side and the positives will be remaining on the other side. Notice again, I didn't say that the positives will move over there. I said the negatives will move over, leaving the nucleus free. So we've got positives on one side and negatives on the other. In other words, we have a polarized object. That's why I said, for us to really get into charging by induction, we have to understand charging by induction, and we have to understand an insulator and a conductor. So in part B, we have now then separated positives and negatives, but because this is really a separable two objects, this third object I'm going to pull away. And so now this, I'll call it the middle object, is negatively charged. And did you notice it's negatively charged with a positive object? See, had they just taken this positive object and touched it, they would have made this object positive. So it's called induction because what you end up doing is chasing off the like charges that you have, and the object you're trying to charge is actually opposite of what you're holding in your hand. Let's see if I can make that happen. Okay, so here's my vinyl. Let's just see if I get enough charge by seeing if I can get it to polarize. So I'll bring it close, chases them down, pull it away, the electrons go back up. But watch what happens when my finger is on here. And I bring it close. Do you see something different? Do you see how the leaf didn't go out? Why not? Now I won't do the whole cycle quite yet, but when I bring it close, the reason they went out is the electrons went down here. But when my finger was on, it didn't go out. Why not? Yeah, because they went onto me. Instead of going down here, they could get further away by flowing onto me. So the electrons don't go down to the leaf, the electrons flow onto me. So what ends up happening here is as I get close, the electrons are now onto my hand, probably even further, my arm and my shoulder. And so if I break connection, they can't get back. And so if I pull it away, now I would say that electroscope is lacking negatives. It's positive, because the negatives are on me. I can put them back if you like. There you go. Now it's neutral. But the polarization, as I said, is a little tricky one, so I'm taking a long time to get here, but I'll put it here. I'll bring it close. They're on me. The negatives are on me. The electrons are on me. I trap them on me, and I pull it away. And once I pull it away, I guess before I pulled it away, did you notice the leaf still didn't go out? And I would say that was because, again, the negatives I had chased off were on the knob. And as long as this was close by, the negatives that were down here didn't want to go up to the knob because this was keeping them from going up. It's when I pull this away, some of the negatives that are down here go up to this knob that's now positive. And so I would argue that that electroscope is now positive. This is charging by induction. I have charged that electroscope without touching it, and I used a negative object, and yet it made it positive. To convince you that it's positive, watch this. Remember, this is negative. So if I bring it near that knob, that should chase negatives down. So what happens to the leaf if I do this? Chased it down. If I get real close, it'll start to move out again because I'll get even, I'll call extra negatives down there. But right now, it's positive. Maybe I should recharge it. It was more positive a moment ago, wasn't it? Let me try it again. So I'll bring it close. Okay, so the electrons are going onto me. I'll trap them on me, pull away. And so now this electroscope is positive. And so, like I said, to convince you that it's positive, I'm going to chase electrons down. And see how I chase electrons down, the leaf begins to collapse? That would tell me that those leaves are positive. See, that's the reverse of this. What if I had done this? Let's go back, 20 minutes ago and just go, well, what if I just touched and swiped? I would say that electroscope is negative because I actually touched it and transferred them on. And to prove to you they're negative, watch this. If they're negative, and I use this to chase negatives down, I would say more negatives, the leaf should move out instead of down. And so here we go. Yep, the leaf moves out. Hopefully convincing you that this is negative. Well, hopefully all this was kind of fun and entertaining, but also educational in the sense that, okay, what do we have? Well, we got a bunch of fun principles here. First one is conservation of charge, right? We know that the electrons, there's not a creation of them or a loss of them, they just transfer. And it's the electrons that transfer around, not the protons. And because of that, we can maybe move them or not. They could either move in the material themselves, a conductor, or they're stuck in that same place on the insulator. And then we can have things that are either polarized, or we can just, the simple case, charge them by contact, or the most advanced case, we can actually induce a charge. That is, we actually make a charge on the object that's opposite to the one we're holding in our hand. And so if we contact it, we make it one charge. If we induce it, we make it the other charge. Well, to make it more fun, I will do this. I can only rub so hard, but this electric motor with a rubber belt up here rubs right up here. And it can rub a lot more than I can rub. And so, if I go ahead and let me try to remove some moisture here. Put the heat gun in here. Get some on the belt. Oh, let me make the belt roll a little bit. So I'll put a little heat here. Little heat here. Kind of fun to watch is to say, well, what would happen if there was a lot of rubbing going on? In fact, this also reminds me of my childhood. I don't know if you ever played this game, but you would take off your shoes and just have your socks, and you would rub until you built up a charge. And then you would go zap your little brother in the ear until he would cry, and you'd get in all kinds of trouble, or maybe you were nicer than me. But that's what we did all the time, is we would like build up charge. And we thought it was great on carpet, and then one day, you know, the world advanced and they started making flooring out of vinyl. Oh my goodness. If you rub vinyl with leather boots, oh my gosh, you can make your little brother cry in one zap. I mean, it just took one little shock of it. And so it doesn't take too much. And so hopefully I have this warm enough here. Because what that shock is, what that spark is so much rubbing that you've built up so much charge that then the negatives come running over here. So if you look at this Van de Graaff, this Van de Graaff has, on one end, is down here where the rubbing takes place, and then the other rubbing. So this ends up getting negative, so the electrons go onto here, so we get a bunch of negatives, and it's taking them off this top one. And so this is negative, and this is positive. And hopefully I can get enough off of here, and I'll turn down a little bit of the lights, but I won't bother to shut the windows, or maybe I'll turn this dark here a little bit. But you can get so much. There you go. That you can really force them across. There we go. There we go. There we go. And so you can get a significant amount of charge, so much so that the negatives come ripping off of here. In fact, maybe you've had that same rubbing going on. Maybe it's the wind. Maybe the rubbing is your feet shuffling on the ground. Maybe the rubbing is, Well, the wind through your hair. Oh, the tumbling of clothes in a dryer. But here is a nice little demonstration of course, what might happen to you and your clothes if they all become the same charge. They get this frizzled hair look. And so these are all positive. In fact, you can see them, they're slightly positive because they're all attracted over here to this negative. And just to convince you, although I will take my phone out of my pocket here, this is a good zap. And so let's see if I can get some of it. Oh, there you go. And so this does make you flinch. And it's quite a bit of a charge. And that's kind of fun to see. In fact, another kind of fun one to see, as long as I've got this going, although I'll come back and try it again on our, oh, it's good, time for a break. But if I go ahead and I neutralize it so I don't shock myself here, and I put a bunch of pieces of paper on here, and hopefully when I take this away, they're going to build up a bunch of positive charges and repel each other from it. And, oh good, maybe I'll work on this a little more and come back from the break here. All right, well, let's call this break time and take our 15-minute break. It's 9:30, so come back at quarter till and we'll keep talking, because now we need to do some numbers. We've done a lot of the concept. Now let's do the calculation. All right, here. All right, good. Hey, okay, well, welcome back from our 15-minute break. Like I said before the break, we should do our numbers. And then I debated before the break, and I decided, yes, I'm going to go back and do it, just because I had shared probably too many silly stories. But this one on the front of the start of the chapter is one of my favorite pictures in this book. When I came across this, I was just like, oh, this is totally it, because here's another family story for you. This could be my son. I remember a day just like this. He didn't have sunglasses on, but he looks a little bit like that, or at least he did back in 1995. He's a lot bigger now. Okay, but in 95, we were traveling, and we left, you know, we live in Ventura, so we left Ventura, we're traveling out. We got as far as the desert. We were in Palmdale, and it was like time to get something to eat and let the kid out. He was getting fussy. He's all locked up in the car seat, and we're like, okay, let's go. There was a McDonald's, so we swing into the McDonald's, and there's like this brand new park across the street. It's got this plastic slide, you know, it's made out of, you know, this plastic and vinyl, and we're just like, oh, this is a perfect place. It wasn't too hot, but it was reasonably warm, very dry, vinyl slide. And so we bought the food, we walk over to the park, and he's about one, and I go to the top of the slide, and it wasn't a curly one like this, it was just kind of a little kid straight one, and I go exactly this. I go, all right, Ryan, your first slide, and I just let him go. And as he goes down this slide, just the rubbing of his pants, I mean, his hair did exactly this. His hair just went, I could just watch him go down. He goes, and then by the time he got to the bottom, it was, you know, just like this was earlier. Just his hair was sticking up like this kid. And to make matters worse, so my wife's down at the bottom, ready to catch him, and he builds up so much charge that there's this giant spark, right? And then, so he gets down the slide, and then just zaps, and he just starts crying. And he would not go on that slide. I think it was a whole nother year before we ever got him on to go on a slide again. I mean, we just zapped the heck out of him. So it was an interesting family story, and one that I hope he doesn't remember. But that being said, let's jump into the numbers. I was kind of showing you conceptual, a lot of stuff, but now the numbers begin, and so let's do some calculations. And I'll start back here with this picture. This is what your author had, trying to show two negatives repelling or a positive and negative attracting. I'll come over here on the board and say, all right, let's look at what Coulomb discovered. And Coulomb then put this into numerical form. Maybe for starters, I will just put the arrowheads up here. And so we know that they're like charges. I labeled them both positive, so they would repel each other. And so number 1 is getting pushed to the left, and number 2 is getting pushed to the right. Let me take you back to last semester. It's called Newton's third law. If object 1 puts a force on object 2, then object 2 puts a force back on number 1, and it's equal and opposite. And so it doesn't surprise you, hopefully, that there's one on each. And they're equal and they're opposite. And so keep that in mind, because Coulomb then is the one who worked out the magnitude of the force. And this is the force on one of them. And notice I say on one of them, it doesn't matter which one. They're equal, but they're opposite. And so you got to solve our problems by looking not only at the equation, but then looking at the picture and go, okay, which way is the picture? Did you notice the first thing I wrote was the magnitude of the force? Because I did not say positive or negative here. And the reason being is one is in the positive direction and the other is in the negative direction. And so this little formula, I want to emphasize, does not have the positive and negative for that reason. This little formula does not need to be divided in half because somehow this is like the total of both of them and you only want to know one, or some silly idea that I get a lot. That's not what this equation is. This equation is the force on one of them. And we're not going to label it as positive or negative because we don't want to limit ourselves to say which one it is. So you're going to have to do both the calculation and the look at the picture. Okay? So this is the magnitude of the force. Now, you could go into more detail like he does and label this something like, you'll see here, here's number 1, and he says this is the force from number 2 on number 1. And all right, if you want to be a little more particular here, we'll say this is the force from number 2 and it's on number 1. That would make this force then from number 1 and on number 2. And so if that helps keep them straight, fine, but I'm not even going to put that. I'm just going to put, like your author does, the magnitude of the force. They're equal in magnitude, opposite in direction. And so what does Coulomb discover? Well, he discovers, first of all, that the amount of force depends on both charges and in the same way. They're both proportional to the charges. So you multiply the two together, and again, let's not pay attention to one being positive or one being negative. Let's just take their absolute value. In fact, I like to do it a little different than your author. Your author likes to multiply them and then take the absolute value. I like to just say, look, let's just take the absolute value of each charge. Let's just talk about calculating the magnitude of the force, and then we'll worry about direction from the picture. And so we'll take the picture and we'll take the calculations. Now, the other thing that comes into play here is how far apart they are. And we kind of alluded to this when we were talking about polarization. We said the reason that when I bring the negative vinyl near this is that it will polarize it, and one of the charges will be closer. In fact, the opposite charge will always be a little closer than the like charge, and because of that, there's a net attraction. It doesn't matter what I bring towards it. I can bring a positive or a negative near it, and it would still attract it. That's why, I don't know if you've ever noticed, ceiling fans or just a desk fan in general can get really, really dusty. And the reason for that is they are constantly spinning and they're rubbing on the air. A lot of modern ones are made out of vinyl, and so they build up some negative charges. The dust floating around in the air is neutral, but neutral will get attracted to the vinyl or acetate. It doesn't really matter whether the blades on the fan charge up positive or negative, they will attract it. And then they stick like crazy. And so one of the dustiest and dirtiest places you'll find is on your fan blades. There's just constantly. On the flip side of that, though, that's a positive. Isn't it cleaning the air? And that's exactly how electrostatic cleaners work. If you were, say, burning fossil fuel, then you would put a smokestack. And in the old days, if smoke just went out the top, and the soot went out the top, and you could see the particles. You could see this big smoke plume. But today you don't see those, because inside those are just layers and layers of metal plates that are being charged, and all that soot sticks to it. It's electrostatically cleaned, and so ultimately what gets out is not soot. We still got the carbon dioxide issue, but we don't have the soot issue anymore. And we got some nitrous oxides, but anything that's not particles. Everything that's particles now is cleaned out before it gets that far. Well, I guess what I'm trying to say is, like Newton's universal law of gravity, Coulomb discovered that it depended upon the distance squared. In other words, if he makes his measurements, and if he takes the interaction between two of them and he doubles it, he finds that the force between them drops by 4, 2 squared. And then when he triples the distance, he finds that it's 9 times less. And of course, there would be some kind of constants in all of this, which we'll refer to then as Coulomb's constant. I'll even put it here. It's 9 times 10 to the 9th. And we just need to watch our units here. We want our answer to come out in newtons. That makes sense. And if we measure in our base units, we would have a meters squared in the top, because we need to measure our distance in meters, so that would cancel off. And we need to measure our charge in coulombs. If you remember the beginning of this chapter, we said that charges would be measured in coulombs. And so what we would do in a calculation is to say, okay, put in Coulomb's constant, then put in the 2 charges that you have, then put in the distance, and get out your calculator, and blah, 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 there's the force. And whether it is a positive or a negative really depends on the picture, because that would depend on which charge you're looking at. It would also depend on whether they're both positive or both negative or opposite charges. And so again, we just want to do a calculation that gives us its magnitude. All right, well, like I said, I think I'll do the same thing I've been doing in the last few chapters, is let me get through the material, and then I'll do some supplemental here this afternoon and do some calculations, because I don't think we'll get a chance in our hour left to really do any calculations, but maybe. But anyways, that's the whole idea. Eventually, that you can put all this together and do the homework. So I'll say it again. This is Coulomb's discovery, and this is Coulomb's law. However, here's where it gets a little more advanced. We call this a field effect. In particular, this is then an electrical field. And I'll change colors here to try to illustrate it, because Coulomb never went quite this far. Coulomb just discovered that there would be a force. And so there's the 2 charges interact, there is a force. But it was some others who went a little further and said, you know, it's a little more complicated than that. There's a little more going on than meets the eye. And the best way I can illustrate it, even though this is a little further than we're ready to go down this road, but if I turn on this radio, see if I can find a talk station.
And they end up caving to these outsiders by crafting new rules of dubious legality.
Okay.
Those most affected, like teachers and students, don't always know what their rights are.
Sadly, I think I found a political station, but forget the political station here for a moment. How does this work? And I'll turn it off for just a second. But what we're going to learn is that somewhere over there somewhere, and probably up at TV, well, I don't know what station I am, but obviously here, we got a lot here at the TV hill here, but there's a broadcasting station, up in the San Marcos Pass there. And anyway, but we've got the huge towers up there. And so what they're doing is the electrical engineers are putting a bunch of negatives up the antenna, and so they make it negative. then they take them down, and they put them up again, and they take them down, and they put them up again, and they put them down. And if you turn to a station like 100 on the FM dial, that means 100 megahertz. That means those electrons go up, down, up, down, up, down, 100 million times every second. And the net effect is then there's going to be this electric field that then propagates to the radio, and the radio picks that up. And so again, a little beyond where we are now, I just want to say that this radio, the way it works is it's picking up the effect of those electrons at the transmitter. So we've got a transmitter, we got a receiver. And if it was just positive charges or negative charges, then this would have no effect. But clearly this does have an effect. And so, like I said, it wasn't Coulomb, but it was Gauss and some others who said, you know, something more is going on than just, hey, you have two charges and there's a force. There is some kind of mechanism that maybe we don't see it with our eyes, but there's some type of process that is then leaving the transmitter and getting to the receiver. And so that's what we're going to call a field. And that's going to be this electric field. I like to draw it this way. I like to say, all right, if this right here is the field, I would say charge number, and I don't know which one we want to pick on first. How about we pick on number 1 first? So charge number 1 creates a field. It creates what you might call an aurora around it, spreading out, radiating in all directions. And so I can't see it with my eyes, but maybe to try to understand it better, I will draw it in orange with arrowheads. And so this is my visual representation of something that I can't see. Somebody was asking me about the different classes and if this one was a hard class right at the end of Physics 110, and I think you were asking, and I said, oh, yeah, I said, well, yes and no. And the yes part of it was, what makes it hard is we're going to be working things that aren't as familiar as a moving car or a moving plane or a moving boat, and because of that, it's harder. Now, there's some other things that made it easier, but I think one of the things that makes it harder is right now is that there is this electric field, and I just got to kind of convince you with experiments that something more is here, because it's not part of what humans detect and humans can see. And so that's this kind of this silly radio demonstration that, hey, there is something going on here. So I'm going to try to draw it with a picture. Your author is going to do the same thing. Maybe I'll flip forward here in his book a little bit, but he kind of starts to draw these, and he draws them in blue. Actually, maybe I should follow his color pattern. Well, already did orange. That'd be okay. Orange. Okay, good. All right. But he says that what happens is around charge number 1 is it spreads out, and what really happens is it's not so much just you have a charge 2, but it's a 2-step process. Charge 1 makes a field. Then the field, as it radiates out, is what pushes on number 2. And so if you were to ask me this question right here, the force from number 1 on number 2 is equal to what? I would say it's really a 2-step process. I would really say that what's happening is first number 1 makes a field, then the field is what puts the force on number 2. So I would say one of the factors that would go right here is charge number 2. Right? How much charge are you going to put there? Because then this other factor is this field. This is the electric field created by number 1. So let's use this symbol here. Let's use E1. Let's use what is the electric field number 1. And so what that means, if you kind of compare this work, like I said, Gauss and others, with Coulomb's work right here, you can see that what you're really saying is the magnitude of field number 1 would be Coulomb's constant times charge number 1 over the distance squared. And maybe just to write it more clear then, the force on number 2 is actually the charge number 2 times the field created by number 1. Here's my warning. We've got 2 charges here. It's easy to get these backwards. It's easy to forget which one is making the field and then which one is feeling the effect of the field. Okay? And so I just want to make it clear. If I'm trying to find the force on number 2, the force on number 2, first of all, comes from number 1. So I need to know the field that's created by number 1, and then multiply it by how much charge am I putting in that spot. Maybe another way of saying the same thing, if this helps, is you can say the electric field is kind of like a unit price. What I mean by that is if you were comparing prices, let's say gas, you would be curious how much it is per gallon, right? You don't really want to compare how much the total cost is going to be, because the total cost depends on how many gallons you get. And somebody in an RV filling it up and somebody in a motorcycle don't even pay close to the same price because they don't get the same amount of gallons. But they do get the same rate, right? They do get the same amount per gallon. And so that's why when you're shopping at the gas stations, you look over there and go, ooh, $6.35 a gallon. Ooh, $6.14 a gallon. I think we come down a little bit, haven't we? Are we down to $5.99 or what's $5.88 in Goleta? Okay. So sad to think that we would say under $6 is good, but wouldn't have been saying that just a couple months ago, let alone a year ago. But anyways, you get what I'm after, I hope. And my point here is we can then think and will think about the electric field as this feature where what you're saying is how much force do you get per one charge, 1 Coulomb of charge. So if I were to tell you the electric field is 14, that would mean I get 14 newtons of force if I put 1 Coulomb of charge there. Just like gasoline, I'll just go with around $6 a gallon. At $6 a gallon doesn't mean your total cost is $6. It's a combination of how much per gallon times how many gallons do you have. And most people get more than 1 gallon, so most people pay more than $6 after pumping their gas. And so that's what this is saying here. And so you can see then in the units, this would be newtons per Coulomb. And so the units for the electric field are newtons per Coulomb. Well, like I said, kind of makes sense. You would say, what does an electric field of 14 mean? It means if you put 1 Coulomb of charge there, you would get a force of 14. If you put less than 1 Coulomb of charge, you would get less than 14. You put more, you'd get more than 14. What you would do is just take the value of that electric field and multiply it by that charge. And that's some of the easier homework problems you're asked to do. Some of the easier ones are saying, hey, you have a charge of, and you put it in a field of, how much force do you get? Now, I probably should say one more important thing here. Since force is a vector, I'm going to put an arrowhead over it. I know at this point in our discussion, I have not been putting an overhead because I've been just saying, hey, let's just calculate the magnitude. But it is important then to realize that ultimately force is a vector, so we got to look at the direction. We can't just do a calculation of magnitude, we also got to look at direction. And that means the electric field has a vector. It means it too is a direction. But here's what your author is trying to illustrate in his pictures. And as we compare picture A, B, and C, here's how we're going to draw our electric field to help us out. To help us out, we'll go ahead and we will, and I'll start with A, say the direction of the electric field, so see all these blue lines and see how they're radially outward? We're going to say, even though we can't see them with our eyes, our definition of the direction of the electric field would be the direction that if you put a positive, they often call it a test particle, a little tiny positive particle nearby it, what direction would it go? So you could imagine that if you put a positive near this positive, let me say right above it, it would push it straight up. If you put it just to the right, it would push it to the right. If you put it just to the left, it'd push it to the left. You put it down here, it would push it down. And so that little tiny positive would be pushed in what I'd call a radial direction. And so what we're going to do is draw arrowheads radially outward. And that's what I have over here. I've drawn them in orange to say, okay, this is going to be how we visually talk about the field. We're going to say it'll be the direction that a test positive particle would be pushed if you had one. And well, I'm not saying you even have one, but what I am saying is there would be a field even without putting a second charge there. It's like saying, if you don't get gas today, isn't the price still $6 per gallon? The price per gallon is still there, but you pay nothing today because you didn't get any gallons. And that's what this electric field is saying. The value is there, but if you don't put another positive around it, there is no force, but there is a field. And so the field is there, waiting, if you will, to put a plus there. In fact, one of the tough questions in tomorrow's lab, I think it's number 14, says, what's the real meaning of an electric field? And hopefully you'll answer it along those two lines. Well, one, it's the mechanism of how the first charge puts a force on the second charge. So it's that process, it's that mechanism. And the other part of it is, its meaning is, how much force would you get per unit charge? Mm-hmm. And those are the two things that the author is looking for in that question. 13 or 14, something like that. Meaning of the electric field. Now look at B for a moment. B is a lot like A, except we have a negative charge. And look where the arrowheads are going, right? Because again, what's our definition? The direction of the electric field will be the direction that a positive would move. And so if you put a positive anywhere near that a negative, it would be sucked in towards that negative. And so it's radially inward. So we will draw lines inward for negative charges and lines outward for positive charges. And then look at this one. This one has drawn just more lines. And that's our way of saying it's a stronger field. Now I want to point out that we've just crossed a little subtlety here, because in Physics 110 we drew the magnitude of a force by representing how long did we draw the arrowhead. And we're going to move away from that. How long I draw it is irrelevant. And that's why they just kind of draw it kind of feathering out. The length of it has nothing to do with how strong it is. We will represent how strong it is by how close the lines are together. And if you take a look at this equation, you'll see that the strength of the field depends upon the charge and the distance away. And you see that in this picture, I think. If you were to move further away and draw a circle at that distance, those lines are further from each other than when you're close in and you draw a circle around it. And so the fact that the lines are close together as you get close to that negative charge is an indication in the picture that we're saying the field is really strong as you get close to the negative. And as you get away back, it's weaker. That's what this picture is trying to say. By the way, did you notice I'm talking a lot about the picture? Because I'm going to say it again. You got to do the math with the picture. It's combining those two together that makes these possible. So you can't just rely on math. You can't just do the old plug and chug and get away with it. You can't just look at the picture either. We got to do some calculations. And so we need to combine those two processes together. Now, if you compare picture C with picture B, you'll see kind of what the author is trying to say, that C, they're closer together than B. And so that would tell me that the field over in C is stronger than the field at B for the same distance away. I mean, obviously it changes with distance. But that would tell me then that they're trying to indicate in that picture that the charge in C is greater than the charge in B. It's got more lines. In fact, I think they got twice as many. Let's see. I'll just do 1, 2, 3 across here, and then 1, 2, 3, 4, 5. Yeah, so they put an extra one in here, an extra one in here, an extra one in here. So there's twice as many lines. The concentration is twice as much. So I would say they're trying to indicate right here that this has a negative charge because it's inward, and it has twice as much charge as that one. Now, it doesn't tell me exactly what they are, but you know, they're not like trying to say, oh, the charge is 17 because they drew 17 lines. They're just trying to say that, hey, if you're looking at two different pictures, compare the drawings and how many lines you have. And that's how we're going to draw this electric field here. Okay, so hopefully that kind of helps, but I must say then, here's where the problems can get substantially hard, is then what about two electric fields? What's the result? So take a look here maybe at this picture. Your author is trying to say that it looks like we've got electric field number 2 on the negative x-axis and electric field number 1 on the positive y-axis. And so this is the result. And so like we did back last semester, right, we've got to look at the x components and the y components and combine them together. Let me help with this picture. I think this picture would look a little better if your author gave you a reason why there was electric field number 1 and a reason why there is electric field number 2. So number 1 goes up in a vertical direction, okay? So if this is our grid, and I'll stick to my orange here, but if the electric field is pointing up on the vertical axis, why? Well, one option is there could be a positive charge down here. Right? We know the electric field points away from a positive charge. So maybe this is Q1. That's one option. Of course, another option is there could have been a negative charge up here. Let me call that Q1. Now let me emphasize there wouldn't be both of them, but one or the other would make an electric field in that direction. Remember, electric fields go towards the negatives and they go away from the positives. So I don't know which one the author is trying to indicate made the field. It doesn't really matter. I just wanted to draw that picture a little bit better to say, your author is trying to help you combine multiple fields together to get the end result. And I think his picture would be a little better if he said, well, where did those come from? Now, look at the other field, field number 2. Field number 2 is in the negative x-axis. So I'll go field number 1, and over here I'll go field number 2. Okay, now, again, same logic. Why do we have a field number 2? Well, it doesn't show anything in the picture, but I would say one option is that we have a positive charge right there. And it would be pointing away from the positive charge. Another option is we have a negative right here, and it's pointing towards the negative. So those would be our two options there. And so let me emphasize again, I'm not saying there's both here. But to get this combination, we might have these two positives. We might have this positive with that negative. We might have this negative with that positive, or we might have those two negatives. But any of those four combinations would mean that if I'm trying to find the total field at this point, that I have to combine two vectors, or excuse me, yeah, two vectors together. Now, one's in the x, one's in the y, so those were the easiest ones to add together, and that's why your author starts here. In fact, I'll go one step further. Why would you even care about adding these fields together? Well, remember what we said? The field is the mechanism that is going to put that force on it. So what we need to find is the total electric field. And then put whatever charge in that spot, and that will be the force. Now again, your author doesn't put a third charge here, but maybe he should. So I'll do that in red. I'll say, okay, what if I'm going to put charge number 3 right there? See, that's the reason why I want to know what is the electric field at that origin. I want to know what it is because here is what I probably want to find. What is the force on charge number 3? It would be equal to charge number 3 times the field, and I'm going to say total field, where total field is then the field from number 1 plus the field from number 2, and we have to add our vectors together. So sadly, I'll say it again, not to scare too many of you too early, but we're starting with some pretty hard stuff here. Because electric fields are a hard concept. You can't see them with your eyes. And we're adding vectors together. And now, not that we haven't done vectors, so maybe that'll be the easy part. That's the part, again, we were having that discussion when somebody asked me, is this semester easier or harder? And I was like, well, it could be easier for some reasons, and adding vectors together you've already done. So if you feel comfortable with that, it's going to be easy for you. If you never quite caught on to adding the vectors with the forces, now's a good time to catch on because it'll leave you drowning. Okay? And so that's what I need to do. So this is what your author is trying to say. I'm trying to say, I would like to know what the force is on number 3. So in order to do that, I'm going to put charge number 3 in a field. The field, though, is created by 2 other charges, so I've got to add those vectors together. And what if I had 4? Good, you can see the game. I would say, okay, I'm trying to find the force on number 4, and number 4 then is going to be placed in a field that's created by the other 3. And so I would add 3 vectors together to get the electric field, then multiply by charge number 4 to get the force on number 4. What if I had 5? What if I had 6? If I had 7, I think you get the idea. If I had 7, right, 6 of them are making the field, so I have to add together 6 of them to get the total field, and then multiply by that 7th charge that is in that location that I want to find that field. And that's why, like I said, after this I'll do a supplement because it would be nice to see some of these calculations done. This can be a little challenging, but at least that's the concept. Oh, and then the hardest one still from the university physics. What if it's an infinite number of charges? What if I have a rod that has the charge spread out. And then I want to know what is the force when I'm a distance d from a rod of length L. What do I do? Well, in picture form, I guess I would think of this as a little bit of charge 1 plus a little bit of charge 2, charge 3, charge 4, charge 5, charge 6, charge 7, charge 8, charge 9, and I would then use my calculus. Right? Isn't that what calculus is? Isn't that what the antiderivative is? Isn't that what the integral is? The integral is when you want to add a bunch of things together. Right? Doesn't the integral of, say, f of x dx mean take a sum in the limits as delta x goes to 0 of the function f of x and a small distance and add them all together? And that's what you're going to need to realize. So in this problem, this would be really a hard problem. And again, this is why I'll have to show you some examples, but I would probably have to do something like this. I would say, all right, now how am I going to get this electric field? I need to add an infinite number of charges together, which that in itself is hard. In addition to that, it's a vector, so I've got to worry about direction. Now, fortunately for this problem, the electric field is all in the same direction. So the direction part of this one is fairly simple in this sense, that I would say, and I'll do my orange here, that the electric field from this first one, the second one, the third one, the fourth one, the fifth one, the sixth one, the seventh one, the eighth one, the ninth one, are like this. And they keep getting smaller, but they're all in the same direction. So luckily I won't have to spend too much time on that, but I will have to say then the field total then would be something like this. I'd say I'm going to add up a bunch of little tiny fields. So let me call it dE. Now I've erased the equation, so maybe it's worth putting back up here, but remember, the electric field was Coulomb constant times the charge over the distance squared. So maybe I would do this. I would say a little bit of electric field is then coming from a little bit of charge. Exactly. Each of these could be thought of as a little chunk of charge. And then, if I spread it out, then what I could say is the total charge on the rod divided by its total length. This would be kind of a density thing that we kind of did in the last semester, although we did mass density. This would be a charge density, right? This is kind of like a candy bar. If you wanted to know the density of a chocolate, you take the whole chocolate bar and divide by its whole length, but that would be the same as a little charge over a little length. And then if you move the dx to the other side, you could replace the dq with q over L dx. You could also then say that the r is actually this distance away. So you might just call this the x-axis. So then this would be x squared. And then you could say, well, what I'm going to do is add up my first chunk of charge, which is going to be a distance of d away, until I get to my last chunk of charge, which will be d plus L. Now I got to admit, I hesitated to dive too deeply into that problem, but I know you're going to need help on it, and I didn't know if I should do it now or in the supplemental or in some solutions, and probably all three of those is going to be needed. But that is the grand finale. If that looks hard, that's okay, because that is a big step. We went from some little, just adding 1 and 2 fields together, to adding an infinite number. Now I better continue on because we only have about 25 minutes here left in class, and there's still a number of kind of interesting things to talk about, including then this picture, which this is kind of your author saying what I was just saying, that if you had two charges, a 1 and a 2, you would take the field from number 1, so there it is, see how field number 1 is pointing away, and the field from number 2, and see how it's pointing away, and you would add the two together, and that would get your field. And so you just say, what's the total field? Well, just add the two together. And in this case, your author's trying to draw a picture, and I'll kind of draw the same picture. He says, after you start to get more familiar with this, these will feel natural to you, because again, the electric field is the direction a test particle would go. So you can imagine, what if I put a little positive right here? What do you think would happen to it? Yeah, that's the easy one. Both of these positives would push it to the left. And if I put it right here, what would happen? Yeah, by symmetry, they would go to the right. So that's pretty easy. The ones that get a little bit harder are maybe going up like this. And if you're real close, you would think it just shoots it straight up. But as you get further from this, remember this one's shooting it over. So I guess I'd kind of expect the field to maybe angle over something like this. And in here might be a little harder. You put a positive right here, it would be pushed away from this one and away from that one. So it would probably migrate a little bit away from it, but definitely up. And then this one would kind of get it up, and maybe it would do something like that. And I think that's kind of the picture he has here. A bunch of these going that way, kind of arcing around, and trying to give you a gut feeling for this electric field, because again, you can't see these with your eyes. Well, in the interest of time, I'll just flash this picture really quick here, but you could see what would be called a dipole versus a bipole. So this is what we were just looking, a bipole, because there's two identical charges, but this is a dipole because there are two opposite, and it looks like equal in magnitude. See how they drew the line concentrations? If I draw a little circle around that one, a little circle around that one, they seem to be the same concentration, so that would tell me they're talking about the same magnitude of charge, but the arrowheads are opposite. So magnitude's equal, but opposite in direction. And because a positive would get pulled over to this negative and pushed away from this positive, in this area it would go something like this. I don't have a good name for it, although I do refer to it as the watermelon shape. And so it kind of gives us a watermelon look to what does this electric field look like. And again, your author is just trying to get you some kind of real gut feeling for all of these. And like I said, your challenge is going to be partly to get a gut feeling and a conceptual picture, but another big piece of this will be just, hey, what is the, calculations? And like I said, I'll have to do some of the calculations in the supplemental. But I do like what your author does here. He has a little section here on, why would people in the life science be concerned or interested in this? I mean, when they're not going into electrical engineering. But here he starts off with a nice DNA strand and mentions the proteins that I know the C is connected to the G and the A is to the T, but and there's some big name, and I don't know what the name is here. You guys probably know it better than I do. But the point is that they have these opposite charges, and all this interaction on a biochemistry level is all this electrical charges. And so all of our chemistry, and mostly our water chemistry, which means our life science stuff, is all done with that interaction. And so I'm glad your author talks about that. And he also then points out then that water is probably impossible to understand if you don't understand electrostatics. Because what happens with water is this oxygen sucks that electron like crazy. Maybe I should draw a picture here. I don't think his picture did justice, but oxygen loves electrons, and so it will grab that electron from the hydrogen and keep it mostly to itself. And therefore, the oxygen part of the molecule tends to be negatively charged, and the other side of the molecule tends to be positive charged. And I say the other side, there's actually, as you know, two hydrogens, but I guess a picture might look something like this. But then we often put a negative on this side and a positive on that side because the molecule is going back an hour. We would say it's polarized. We would say everything has been brought over. And so there is this positive and negative to it. And because of that, the way this water molecule then interacts with other water molecules and other elements like sodium chloride, like DNA, makes an important difference and literally makes life itself here. And so that's kind of what your author is getting at here. Now, he takes this even one step further and says, what happens to an electric field that's in a conductor or near a conductor? And so remember, conductors mean the charges can move around. And so when we charge this up, when we put charges on them, how did they distribute themselves? Did they go equally in all directions? Well, the first thing that your author argues, and he has it in this picture, is that the electric field must be perpendicular to the surface. Because if it's not perpendicular, it would have a small piece that's parallel to the surface. Remember, that electric field is the mechanism that makes forces move. Remember, conductors mean they move. And so if you have a conductor and the field is at an angle, then what that would do is make charges move along that surface. And the charges would keep shuffling around and moving around until they had no more sideways. In other words, they would move around and change the overall field until they are perpendicular. Watch, his next picture does this much better. Now, he doesn't draw the before picture, but he should. If you take this sphere away and you just imagine an electric field going straight across, and now you put a metal ball in there, the charges in here are going to move around. And then the total field is the original field plus the field that's created by these charges. And what he's trying to argue here is the end result will always be that the field right on the surface will be perpendicular. And again, the argument is kind of an indirect argument. It's if they were not, then there would be a tangential component along the surface. Because it's a conductor, they would move until, and that would change the field. So they keep moving. They keep changing the field until there is no tangential piece. So in this case, if you put this in here, the field's going to arc down because a bunch of negatives are going to race over to here. And you can see now the field gets terminated on the negative, and then over here it gets regenerated. And so a nice property of conductors is that the field is always perpendicular. Now, the same logic is inside a conductor, the field is always zero. Again, what if it wasn't? Well, again, what's the meaning of an electric field? The meaning of an electric field is that it puts a force on them and moves the charges around. So if you ever had a conductor and there was a field inside of here, the field would say, okay, push the charge. And because it's conductive, the charges would move. And they would shuffle around. And as they shuffled around, they would change the field. When would they stop being shuffled around? Well, when there's no more forces on them. And there's no more force on them because the field has gone to zero. And so the whole argument is exactly the same. And so your author is trying to say here that if you had something that was, in this case, round, but it doesn't matter what shape it is. I could have something, I don't have a good metal conductor, but let's pretend this cylinder is a metal conductor. What I can say is inside of here, there is no field. And then whatever field it does have, it's perpendicular right on the outside surface. So outside surface, it's perpendicular. Inside, zero. And that's kind of this argument of this whole electric field thing. Now, he does this kind of quick, and I guess I'm going to have to too, and maybe rightfully so. It's a little too much here in the first chapter. But if you just had a metal plate and another metal plate, those two metal plates will make a nice uniform field right in the middle. And so we're going to use this design a lot. It's kind of the best way, an easy way to engineer anything. It's like, hey, you've got a nice uniform field. Whereas if you solve for the point, as you got further away from a point, the field got weaker and weaker. But if you have a big metal plate and another metal plate, you make one positive and one negative, you're going to make a field that goes from positive to negative, and inside is going to be uniform. Now, on the edges, you can kind of see how a positive would kind of maybe arc around like this. But in the plate, you can see how a positive would just go, doesn't matter where in the plate, as long as you're not near an edge, it would just go kind of straight down. And so that's his argument about the field. And so he spends a little time here trying to get you a gut feeling of what does the field look like in a conductor. Now, this might be the hardest one of all. What if you have what he calls an uneven shape? And he looks like he draws an egg. Okay. I don't have an egg, but I have this piece that is kind of uneven in this sense. It's more rounded here than on the top. And in fact, it even has a little bold knob at the top. And he argues then that the charges build up on the sharp points or the edges. Maybe the easiest way to explain this is think for a moment as you and I as the electrons on a sphere which we call the Earth. So here I am on the Earth, I'm on this giant sphere, and remember that we repel each other. We're all negative. So that means we're going to want to spread out. But what's interesting is if it's a curved surface and the field does not go into the conductor, I cannot, once you go what I'll call beyond the horizon, so if you were to get on a boat and get in the ocean and sail over to Japan, you don't have to go that far, but go all the way to Japan, there's no way I can see you. There's no way my electric field can penetrate you. The only way my electric field can have an influence on you is if I went through the Earth, because Japan is probably, where's west here? Probably like that. I mean, that would be the straight shot to Japan. But my field can't do that. So an electron that's over in Japan will not feel my presence, and therefore will get closer. Doesn't even know I'm here. And if you keep coming, I don't know, where do you get to? Midway Island and Hawaiian Islands, and eventually you get to my horizon. And once you come up above my horizon, now my electric field, because it doesn't have to go through the Earth, can start pushing you away. So you'll go beyond the horizon. So the more curved a surface is, the shorter you have to go to get beyond the horizon. And so they can get really crowded. And that's what he's trying to say here. And so on this pointy end of the egg, there's a lot of positive charges. And on the less pointy end, there's less charges. But they're still there. And notice there's hardly any along the flat edges. And that's why this thing is designed the way it is. There's going to be quite a bit of charge along this surface and pretty much even along here. Almost no charges on this flat part and a lot on this pointy top. In fact, it's why I brought out, I think I'll have enough time here to show you this next picture, but he shows you a really sharp one. And it could be so sharp that they can come shooting off. They're so close together, and that's what this little mechanism is. This thing has little sharp edges on it, and they will come shooting off. And as the electrons come shooting off, even though I can't see them on my eyes, remember the equal and opposite? It'll spin this like a wheel. And so I will begin by saying, all right, if I have it dry enough, see if I can build up enough charge. Oh yeah, good. Let me neutralize it. Let me put the little doohickey on here. And it won't be much, but can you see it begin to turn? And it'll get enough charge. In fact, it's shooting them off. They're all racing to that sharp point and shooting off that I won't even get a spark over here anymore. They all raced up to that sharp edge. On the other hand, I take that away. Now they'll build up on this sharp edge on the top. And I'll get my spark back. And so I've got a little impulse engine, if you will. But I also have my lightning protector. I got a little sharp edge that will then build up and then get the charges off to hopefully keep my building safe from a lightning strike. One of Franklin's inventions here was to protect buildings from lightning strikes here. Well, then your author takes a few moments to get into some applications, and so this will be actually a good place. I think our timing is going to work out just about right. Oh, shoot. Yeah, I'll take the time. Okay, remember how I told you that an electric field does not get inside a metal container? So these pie pans are kind of fun to watch, because what I'm going to do is I'm going to place it on top and turn it on. And because they're made out of metal, the charges will flow from this ball, and it will actually go on the bottom plate, and then the next one, and the next one, and the next one, and the next one, and eventually the top one will get charged. But here's what I want to convince you of. They will all be charged. However, remember that it's not just that they have charge. If they were all charged, you remember this little confetti that just like flew apart because they all got charged? You might think that would happen with this one because they would all get charged, but because they're metal and they come over the edge, the top one then blocks the field from the other ones. So even though they have charge, they don't have a field to push them off. And so there'll be a stack of like charges, but they won't repel because there's no field except for the top one. So only the top one will get pushed off, which will make a new top one, which will then get pushed off, which will make a new top one, which then will get pushed off. And so it's kind of fun to see this because it illustrates then how the field really is the mechanism that puts off the force. It's not just all at once and a big confetti piece. And so that's kind of a good picture of the field being protected because you're inside the conductor. It's called a Faraday cage, by the way. And so if you've got some free moments, I would encourage you on YouTube, just Google Faraday cage, music, lightning, and you've got some very risky, crazy band members who are dressed in like this metal chains. That's their metal outfit. And they're playing underneath one of these giant Van de Graaffs, and these lightning bolts are just coming down and striking them. But they go over the metal cage, not inside the metal cage. And so they get struck with these lightning bolts, and it's very wicked to see. And but they're well protected, at least in theory. Bit risky in case something goes wrong, but like I said, kind of fun to see. All right, well, I'll stretch the last few minutes. Here's the Van de Graaff one. I'll kind of skip that one and go to one of my favorite ones. Here's a photocopy machine. We're a little early to talk about the photoelectric effect, but one of the ways that a application of this is you have this drum, either aluminum or a selenium, and what you do is you take this drum and you rub it. Now, you don't personally rub it, you just walk up to a photocopy machine, put it on there and hit copy. But this little drum then gets rubbed and it builds up an electric charge on it. Then what happens is you put your whatever you're trying to make a copy of. So here's this piece of paper with the number 3, and you'll probably notice in a photocopy machine that there's this light. Sometimes it's a light that scans across, sometimes it's a big flash of light, but the light's important because the light goes up and reflects off your piece of paper and then goes on this drum. And the drum rotates, and so as the light goes and scans across and reflects, the light's going to come down and the light will bounce off your paper except where there's writing. So on this piece of paper they have the big number 3. And so light reflects everywhere except where there's the black number 3. And when the light hits the drum, this is called a photoelectric effect, it actually kicks off the electrons that were now stored on this aluminum drum. And so I don't know if you can kind of see, but these are supposed to be the charges. And see how there's a number 3 of charges still left? See, the whole thing was originally completely charged. And then after the flash of light or the scanning of the light and the rolling of the drum, there is now a number 3 here. And then what's nice about that is then you can take some little tiny pieces, you would call it toner, but they're really pieces of black ink, black plastic. And so like these little confetti pieces, they're neutral, and won't they stick then to the positive drum? And so what happens is it sticks everywhere there is a positive. And so that's what this is saying. And now to help it out, they'll make the toner negative. So you got these negatively charged toner that sticks to the positive, and it makes a number 3. And then you take a clean piece of paper out of the tray and you roll it across, and that then presses the toner into that piece of paper, and then usually you warm it also a little bit, and that melts it in. So you probably notice when it comes out of the photocopy machine, it feels warm. And so you see both a flash of light and a warm piece of paper that comes out. And sometimes if things aren't working quite right, the paper will actually feel a little staticky. It'll be warm and staticky, but it does come off, and it's supposed to go through a discharging area, and that makes it, you can kind of see as it comes out, there's like these little felt pieces rubbing on the paper trying to take all the charges off of the end of the copy machine. Well, some other fun ones to do here is a laser printer is exactly the same way, except this big flash of light is not there and you don't have an original. What you do is you just charge the whole drum here, and then if you want to print like the number 1, you then just take your laser beam and you shoot the laser beam everywhere you don't want writing. Remember, because the laser beam, the photoelectric effect is going to take it off. And everywhere you don't want writing is where you shoot the laser beam. And so then you just have the number 1 with a positive charge on it. And then you do the same thing. You put a little negative toner, you put a piece of paper, you roll it. And so a laser printer will also come out warm. Again, but you don't need an original for that. But you need toner. Now, that's slightly different than an inkjet printer. Here's the inkjet printer, which probably most of us have, unless you do a lot of bulk printing. But, you know, in our lab, we have the laser printer, but at home, I've got the inkjet printer. The inkjet printer works kind of the same way. You just have a little nozzle that shoots tiny little droplets of ink, and then you control them by running them through an electric field. And so in this case, the electric field is deflecting them up and down and then going to make a pattern of the letter A. In fact, you can kind of see that effect right here with water. Remember we said water an important one to you guys who are in the life science, because it has charges on them, or it's polarized, I guess is the word I'm looking for. And so if I go ahead and want to control or deflect the water, I can do that with an electric field. And so just like the inkjet printer is deflecting the little droplets of ink, I can deflect the water with my pen. And so just by bringing it near, I can actually, you know, swiggle the beam and draw out my name, M. All right, I won't do my whole name, but I can see it as it hits the bottom of the sink, because I can control where it's going. And so again, a lot of very useful applications. And this one I mentioned already, and so I won't say too much to it, but here is how we clean our air now, and now we've gone a little better in our industrial age. We don't just let the soot go shooting out the tops of the smokestack. It comes up, and there's a filter after filter after filter after filter, and you make the filters positives and negatives, and you do all kinds of things just to trap it all. And so by the time it comes out the top, it doesn't have any particles in it. No more soot is there. Like I said, there's other things, but no more soot. And I think, that's good timing, because that's the end of our applications. And so my next step is to maybe add some supplemental problem solving, because these can be tough. I shouldn't keep saying that, because I'm just going to scare you guys. All right. Well, it was a good first lecture. And I'll say bye now for both you guys in person and you guys online. And remember, no lab today on our first one, but our first lab will be tomorrow, where you guys will do exactly what I was doing, where you kind of rub the vinyl, the acetate, the electroscope, and whatnot. All right, see you guys later.